I'll just get right into it then. So thank you very much to Jan and the organizers for putting together a really fantastic workshop, now 5 years running. It's a great resource for the community, and I really appreciate it. Thank you for sticking to the bloody end of this session today. That's late for some of you and very late for some others of you. And a gentle plea that if you're decent and you're not doing dishes, maybe consider turning on your camera, because I love to see all your faces. And it prevents me from slipping into solipsism, which does not make for very good talk. So with that, I'll get into it. So I'm David Sivak. I'm here at SFU Physics. This is a shot of our campus on a mountaintop looking out over the howling wilderness next door. And if you get nothing else from this talk, I hope to be able to convince you that sheep trading can tell us something about non-equilibrium thermodynamics in molecular machines. So I'm really interested in molecular machines. I think it is full stop amazing that nature has figured out how to do energy conversion using floppy soft goo. And I'm really fascinated in trying to think about how that works. And so what do molecular machines do? So they convert between different energy types. So here are some canonical examples. There are light harvesting machines, such as Photosystem 2, that receives incident photons originally from the sun, uses that energy to split charges, to split water, that then gets translated across a membrane to achieve charge separation, essentially a voltage. So this machine is converting sunlight energy into electrical energy. Perhaps my favorite machine, ATP synthase, uses a voltage across a membrane, in this case, created by Photosystem 2 or other systems, and it converts that energy into rotation of a central crankshaft axle that then pushes on a second subunit, F1, to make ATP. Now, ATP is a high-energy, portable, long-lived molecule that essentially can be transported elsewhere in the cell, and it drives various other energetically unfavorable reactions, such as transport. So transport motors such as kinesin. Here's an artist's depiction of the motion of kinesin that hydrolyzes ATP, uses that free energy to then transport relatively large cargoes along cytoskeletal filaments in a directed fashion. So it's converting chemical energy into mechanical motion. And so one thing that's interesting about all of these machines is that they're built of distinct components in a way that human engineered machines are. And these components often interact with fairly distinct aspects of the environments that they're embedded in. And so what I want to pose today is the question of thinking about how do interactions between those different components, how does internal transduction of energy and information constrain, limit the external performance, the actual functional behavior of these machines in terms of their impact on their surroundings. And so this is work that was conceived, carried out, written up exclusively by really talented members of my group, Matt Layton, who's a current PhD student, and Yannick Eric, who's now a former postdoc in the group, that you can see the details on this preprint. And so we're really starting from essentially the simplest way of analyzing molecular machine behavior, a very popular mode, which basically just treats them as a black box and says, look, I've got some system, my machine, I've got inputs and outputs, and I want to sort of understand how those work. So in the case of ATP synthase, I might have input work into this machine in the form of protons being translocated across a membrane to drive this machine. I'll have some output work in the form of ATP being synthesized. And then I have thermal interactions with my surroundings. So I have heat flow in general in and out of my system. And we want to resolve this a bit more to understand something about sort of architectural principles, internal behavior of this machine. But we're theoretical physicists, so we don't get too carried away. We basically zoom in to resolve these machines into two different components. And to keep things simple in the presentation here, I'm going to assume steady state behavior and bipartite thermodynamics, that the fluctuations of the different components are independent. You can generalize that picture, but I think the most intuitive results emerge from this framework. And so we have FO, one of the subunits of ATP synthase, that receives input work, these protons going down their gradient. It's also in thermal contact with its surroundings. And then F1 is producing the output work, making the ATP, doing the chemistry, and it also experiences thermal fluctuations. And now we need to resolve something about the interactions between the different subunits, right? So in general, there's an energetic interaction, there's work or energy passed between the two different subunits, a transduced work, and there's also an information component, an entropic component to their interactions, what's known as an information flow. And this framework really takes inspiration from a really beautiful paper from our host, Udo and Andre, our speaker from this slot yesterday. And we've reviewed last year with Yannick sort of some of our recent thinking about this framework. But let's talk a little bit more about this information flow. Like, what is this quantity? So literally, it's the rate of change of the mutual information between the two different subunits. So loosely speaking, the correlations between the state of FO and the state of F1, how is that mutual information changing as FO dynamically evolves? So loosely speaking, what are the correlations that FO creates or consumes with F1, right? How does it increase correlation or decrease correlation with F1? And this mutual information between the two is a thermodynamic resource. So in the same way that in a single dimension, reduced entropy is a thermodynamic resource, and the most visceral way that I think of this is I've got a biopolymer, for example, DNA. It's attached on one side to a surface, on another side to a bead that, for example, with an optical trap, I can manipulate. I can stretch this polymer. The polymer isn't energetically unhappy. It's just entropically unfavorable because there are very few conformations of this polymer that can achieve the long extension. So if I let go of this bead, in general, this polymer is going to compact, it's going to increase its entropy, and that's very much an entropic driving force pushing this behavior forward. So reduced entropy is a thermodynamic resource, as many of us already appreciate. And so similarly, in a multivariate setting, mutual information, or reduced joint entropy is a thermodynamic resource. So you have these two components of how the two different subunits communicate with each other, and they combine using first and second laws applied at the level of individual subunits. We can combine those first and second laws, and we can get bounds on the input work, a lower bound on the input work, and an upper bound on the output work, and the same quantity appears bounding both of these quantities. So it is the transduced work rate, and then the information flow modulated by the temperature of the thermal surroundings. So we call this a transduced free energy because it has energetic and entropic components just like a conventional free energy. And so you've basically got this bottleneck quantity, this transduced free energy, that mediates between how much work you need to consume and how much work you can put out. So it's a thermodynamically important quantity. And we've made use of this to think about subunit level efficiencies and how you infer those in actual experiments. I'm not going to talk about that today. What I am going to talk about is elaborating this picture one step further, motivated by the observation that not only do different components of machines generally interface or couple to different aspects of their environments, they often experience fairly different strengths of fluctuations or different spectra of fluctuations. So take the example of photosystem 2, right? It receives these highly energetic photons from the sun that are way off scale compared to the thermal fluctuations that the machine as a whole experiences from jostling from its surroundings, right? So that moiety in this machine that actually absorbs the photons is subject to a very different spectrum of energetic fluctuations than the rest of the machine. Likewise, if you think about these transport motors, they're acting, they're moving, they're consuming energy and doing directed motion in the context of many other motors that are doing similar kinds of things. And those motors are not only channeling free energy into motion, they're also just dissipating energy into their surroundings. In general, they're kind of stirring the pot, right? So the cytoplasmic solution, the medium in which these machines move, is not just a thermally fluctuating medium, it has so-called active fluctuations. And there's no reason to think that the different parts of this machine or the machine assembly will experience to the same extent, these active fluctuations. This very large cargo might be much more prone to getting jostled by these active fluctuations than the machine that's relatively small and relatively shielded by the filament. So these are examples that are meant to motivate the idea that we should be thinking not just about components of machines that are all in contact with a single source of fluctuations, but actually that they actually harness different fluctuations. And so the simplest way we had of conceptualizing this was just to say, well, let's say that each component is in contact with a thermal bath at a different temperature, right, to represent these different strengths and fluctuations. Okay, so that's really the additional elaboration to this picture. And you can turn the crank, you can do the same kind of analysis, you can apply the first and second law at the level of each of these components. And when you combine them appropriately, you once again get bounds, lower bounds on the input work, upper bounds on the output work, but there's no longer a single bottleneck anymore, right? You have different quantities that form these bounds because you're now combining the energetic and the entropic components of the communication between the subunits in different ways due to this different parameter that naturally combines them, the temperature that the given subunit is in contact with, right? So how do we think about this now, right? In this context where essentially energy and information have different relative values to the different components of this machine. And so to get intuition for this, we sort of took a step back and built up an analogy that I want to present to you now. So think about a heat engine. What is a heat engine doing? It's taking heat from a high temperature bath, and along with that heat comes entropy. It is outputting heat to the cold thermal bath, ejecting entropy along the way. And then the difference in those heats, it can then output as useful work to its work medium. And so the key point here is that different heat baths exchange entropy and energy at different temperatures. So they have different prices, if you will, for the energy in terms of the entropy that comes along. If you want to extract net work from a heat bath, you have to transport entropy between the different heat baths. If you don't do that, then you can't have any net output work. The economic equivalent is a context that's known as arbitrage. So if I have a trader, in this case of sheep, that has access to two different markets with different prices for the sheep, then how can they make money? How can they have the equivalent of net output work? They can buy sheep in the cheap sheep market. They can sell the sheep in the expensive sheep market, and then they can pocket the difference in profit, right? And so the equivalent points here are different markets exchange sheep and money at different prices. And therefore, the design principle is that if you want to make a profit, you have to transport sheep between the different markets. Otherwise, your scheme doesn't work at all. So now elaborate this picture of arbitrage one step further to be more parallel with this bipartite molecular machine setup. And now imagine that I have an arbitrage partnership, right? So each of the partners only can trade in one of the markets. So what's the strategy now? Borrow money from the bank, buy the sheep in the cheap sheep market, send it to your partner, and now trade the sheep in the expensive sheep market and redeposit the money that you make at the end of the day. Okay, so what's the design principle here? If collectively this partnership wants to make a profit, they have to transport sheep between the two of them, right? Otherwise, the scheme doesn't work at all. You can't achieve this at steady state. So now step back to this bipartite heat engine context. And what if I want to extract net work from this bipartite heat engine where one component each is in contact with each of the heat baths? To extract net work, I have to transport entropy between the heat baths, of course. And the only way I can do that is between the different components of the machine. And the only way I can do that is through this information flow quantity. Okay, so the upshot is I need to have information flow between the subunits to support net output work or a functional heat engine. Okay, so that's the intuition. Again, you can take the first and second laws in this context for each component. You can smush them together, combine them in the right way, and you get what we call an information flow arbitrage relation. So what is this saying? This is saying I have a upper bound on the net output work I can achieve, right? Due to the signs, these are minus W's due to the sign convention. The net output work is upper bounded by the product of the information flow between the two different components and the difference in temperatures between them. So what this is telling you is it's telling you that if you have a heat engine that is bipartite in this sense, in order to be functional, it must operate at least implicitly as an information engine, communicating information between the two different subunits. Conversely, something that was already appreciated, if you want an information engine that can achieve net output work and be functional in that way, it has to operate as a heat engine across a temperature difference in order to actually do anything useful. So that's the math, that's the theory. How do we see this in operation? How do we sort of illustrate this? The simplest example we came up with was a two-dimensional ideal gas undergoing a Carnot cycle. So imagine a two-dimensional box. You have gas molecules whizzing around. Let's say they're monatomic, so there's no coupling of the energy between the different degrees of freedom of the gas molecules. And I hold the top walls of this vessel at a cold temperature and the side walls of this vessel at a warmer temperature. So here's my cycle. I put a vertical partition into my box, and then I compress each side of that box in a different direction. Okay, I know how much work I need to do that isothermally. I then swap which of the partitions are mobile. I immobilize the horizontal partition, I mobilize the vertical one, and now I expand using work from the gas in opposite directions on each side of the immobile partition. Isothermally, I know what work I get out from that. And then finally, to close the cycle, I swap the partitions. Okay, so the thermodynamics of this is just the thermodynamics of the conventional Carnot cycle, but you can look at this in an information theoretic way as well. Okay, so you can actually draw these energy flows and information flows between the different components. And so let's look at this under this lens, the reaction cycle. In step 1 to 2, what you're doing is Y's dynamics are correlating it with X. They are building up mutual information between the two. Y you can think of as a memory that's encoding a measurement of X. And then in step 3 to 4, you're taking advantage of that measurement. You're using information about X encoded in Y to apply feedback and move the pistons in the appropriate direction, leading to an apparent violation of the second law. So this is kind of a Szilard engine analog. If you look at the level of subunit X, all it's doing is receiving heat from its environment and outputting work, which should be forbidden by the second law. And of course, the second law is not broken. It's saved by the fact that you have this information flow between the two different subunits that's saving the day. Okay, we've done a similar analysis for the Brownian gyrator to show that it, a sort of conventional stochastic thermodynamics model for a heat engine, is also an information engine under the hood. And the double quantum dot information engine is also a heat engine. Finally, you can invert this information flow arbitrage relation, and you can use it to put bounds on the information flow, which is a quantity that's generally not tractably measurable in experiments. So let's look at photosystem 2. Let's expand our resolution of our model to take into account energy and information flows between the subunit that receives the solar energy photons and the subunit that does the chemistry to split water and dissipates heat to its surroundings. And you can rearrange our information flow arbitrage relation to now a lower bound on the information flow through this machine, constrained by the actual observed output work rate and the temperature difference. So we can plug in known numbers for this: the temperature of the surface of the sun, the temperature of the body, the known throughput rates and thermodynamics of the reaction that's catalyzed. And what you get out is a pretty surprisingly high number, an information flow of at least 2,000 bits per second through an individual photosystem 2 molecule that comes out to about 7 bits per reaction. Okay, that's a bound. What we've also done is we've taken a popular stochastic model for photosystem 2 that's been parameterized by other people against experiment, and we've run the calculation to actually say what is the information flow in this model, and we get about 9 bits per reaction, which is close to but greater than this lower bound. We've done a similar analysis for bacterial rhodopsin, where we've gotten somewhat smaller but still surprisingly high information flows within this machine. And I say surprisingly high because similar kinds of analysis have been done in very different contexts. For example, cellular signaling networks, often related to some of the chemotaxis behavior that we heard about a couple talks ago, and they find orders of magnitude smaller information rates than the kinds of rates that we are inferring here, that we are calculating as bounds. Okay, so with that, I'll just briefly show the current state of my research group, highlighting Matt, that actually co-led the research here today. I'll just mention that we're always interested in talking to people who find these ideas exciting. So speak to me if you're interested. We're currently interviewing for postdoc positions, and we have openings for grad students and summer undergrads. And finally, just to bring up the summaries here, molecular machines are fascinating and they make life go. It turns out you can derive that internal information flows bound the output energy that a bipartite molecular machine can achieve. So successful or productive functional heat engines are implicitly Maxwell demons, and this gives you a new avenue to possibly doing thermodynamic inference, in this case of internal information flows. So with that, I thank you for your time and welcome questions.